It's not easy to become a famous mathematician these days. It was probably even harder back in the 1700s, but that's exactly what Euler did after solving this problem. And when I say solve, I don't mean the approximate answer, I mean the exact answer. Anyone can start just adding up these numbers and get pretty close to 1.64, but that's not exactly satisfying, is it? There are many ways to solve this, but let's do it the way that Euler did that brought him immediate fame. Start with the Taylor series representation for sine x. This is something you probably see in Calc 2. Divide both sides by x, so we have sine x over x as this new representation. And I want you to pay very close attention to the coefficient of the x squared term. That minus 1 over 3 factorial, that's minus 1 over 6. That will come up later. Remember the good old fundamental theorem of algebra? We can factor polynomials into linear factors using the polynomial's roots. Now think about how you factor basic polynomials. Typically we think of two numbers which multiply to the constant term. The constant term of our polynomial is 1, and it's an infinite polynomial, so the numbers here all have to multiply to 1. The only way that that's going to work, unless we want to use a bunch of fractions, is to make all the constant terms in the linear factors 1. And we know when we plug in the roots, the zeros of the polynomial for x, it should be 0. So each factor should be 0 at one of the roots. What are the roots of this polynomial? Well, it's tough to see on the right-hand side, but if we look at sine x over x, well, that's 0 when the numerator is 0, and sine x is 0 at n times pi, where n is an integer. Well, we can't have 0 here, otherwise we'd be dividing by 0, but every non-zero integer multiple of pi will be a root of this polynomial. In other words, when we plug in plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on for x, we have to get zeros at one of these factors. The way that we do that is make it 1 minus x over the root for all of the roots. And so we have the factorization here. If you're up to date on your factoring formulas, you may notice that this is factored into a bunch of difference of squares. So each pair we can combine into 1 minus x squared over the root squared, and we have another factorization representation. If we were to multiply this all out and then collect all of the x squared terms, pull out the x squared term, the coefficient of the x squared term would be the minus 1 over pi squared, minus 1 over 4 pi squared, minus 1 over 9 pi squared, and so on. So the coefficients all have a negative, they all have an over pi squared. Factor out the minus 1 over pi squared, and what we'll see is that coefficient is the sum we were actually asking about in the first place. So the coefficient of x squared is minus 1 over pi squared times the sum from n equals 1 to infinity of 1 over n squared. And since the equations are equal, the coefficient of the x squared term on the left has to be the coefficient of the x squared term on the right. This is sometimes called matching coefficients. And so now all we have to do is solve for the sum. 1 over 3 factorial, that's 1 over 6. Cancel the negative on both sides and multiply by pi squared, and there we have the sum from n equals 1 to infinity of 1 over n squared as pi squared over 6. It's pretty incredible.
What's 1 over 1 plus 1 over 1 plus 2 plus 1 over 1 plus 2 plus 3, so on forever? This problem feels very reminiscent to the sum of the first n natural numbers, 1 plus 2 plus 3 plus 4 all the way up to n. We can solve this pretty quickly using induction, or more simply, write this sum as s backwards. Add it to itself, so we get 2s, and the way things pair up is very nice since we get n plus 1 n times, since there were n terms. So we can solve for this sum by dividing by 2. S is just n times n plus 1 over 2. Although sometimes it's more convenient to write it in summation notation. I would probably write this as the sum from k equals 1 to n of k. This means the same thing as 1 plus 2 plus 3 plus 4 all the way up to n. Now, this wasn't the question I originally asked. I was interested in the reciprocal of this. Well, not exactly the reciprocal of this, but something pretty similar. What we can notice is that we can write our sum in question using this summation notation. We could write it as the sum from n equals 1 to infinity of 1 over 1 plus 2 plus 3 plus 4 all the way up to n, which is this summation we just found. So instead of using the summation notation twice, let's just replace it with this formula. So it's 1 over n times n plus 1 over 2, or more simply, we want to calculate the sum from n equals 1 to infinity of 2 over n times n plus 1. If you've taken calculus, it wouldn't take you too long to figure out that this is indeed a convergent series. Say, compare it to a p-series with p equaling 2. But that doesn't exactly tell us how to find the sum. What we can do is the partial fraction decomposition. Let's factor the 2 out from the numerator, and let's figure out how to break up the fraction 1 over n times n plus 1. This should break up into two fractions as a over n plus some b over n plus 1. There's many ways you can go about doing this. I would probably multiply by the quantity n times n plus 1 to clear all the fractions. We can distribute and combine like terms. And here we do what's called matching coefficients. The coefficients on the left have to match the coefficients on the right. Doing that tells us that a has to be 1 and b has to be -1. Now we're interested in finding this sum, and this is what's known as a telescoping series. That's because if we write out the terms, things start to collapse like a collapsible telescope. Writing out the terms of the series, we would get 1 over 1 minus 1 over 2, then 1 over 2 minus 1 over 3, then 1 over 3 minus 1 over 4, and so on forever. But if we were to stop writing terms at some point, the pattern would look like this. The 1 over the 1 would never cancel out, but all of the middle terms would. We'd be left with just minus 1 over k plus 1, k being the number of terms in our series we wrote. This is what's called the partial sum, and it lets us find our infinite series by taking its limit. Fortunately, if we take the limit as k goes to infinity, that piece disappears. We just get 2 times 1, or 2. Start with an equilateral triangle. Next, divide the sides into 3 equal segments. Draw more equilateral triangles, so the middle segment of each side is the base of the equilateral triangle. Remove the base of each mini equilateral triangle, and repeat this process indefinitely. Take each side, break it up into 3 equal segments, draw an equilateral triangle on top of the middle segment, then remove that middle segment. This is what's known as the Koch snowflake, and it's one of the earliest fractals to have been described. What I love about it is that its properties are a little paradoxical. Let's look at the perimeter of this object. To find the perimeter, we'll have to describe each iteration. The first iteration would just be the base triangle itself. This would be the second iteration, the third, and so on. We'll have to know how many sides are present at each iteration in order to find the perimeter. Let's let capital N sub n denote the number of sides at iteration n. The way that this pattern works is that each side is then replaced with 4 sides. So we could say that the number of sides of the nth iteration is the same as the number of sides of the previous iteration times 4. We start with 3 sides to begin with. Every iteration, we multiply the number of sides by 4, so the number of sides of the nth iteration should be 3 times 4 to the n. What about the length of each side? Let's let capital S sub n denote the length of each side after n iterations. Now we didn't specify the length of the side of the original triangle, let's just call it little s. And since we divide the side lengths in thirds, every single iteration will divide each side length by 3. So s sub n should be s over 3 to the power of n. Now we can find the perimeter. The perimeter of this shape, I'll call it P sub n, the perimeter after n iterations, should be the number of sides times the length of the sides. That's just 3 times 4 to the n times s over 3 to the n. You could rewrite this with properties of exponents. Let's just call this 3s times 4/3 to the n. This is our perimeter after n iterations. So you might be wondering, well, what happens if we just do this process forever? What if we take the limit as n goes to infinity? After we do an infinite number of iterations, what do we expect the perimeter to approach? Well, taking this limit, the quantity 4/3 just keeps getting larger and larger. 4/3 is bigger than 1. Multiplying it by itself over and over is going to get bigger and bigger, and so the limit of the perimeter is infinity. This perimeter should be unbounded. Here's the paradoxical part. What if we look at the area of this object? Since we're talking about area, we'll have to know how many triangles there are, not just the number of sides. Let's let capital T sub n denote the number of new triangles added in the nth iteration. Well, the new number of triangles we add just depend on the previous number of sides. We start with 3 sides and we add 3 triangles. So T sub n is actually capital N minus 1. The number of triangles added is the number of sides from the previous iteration. And we already had this value. Just a quick bit of algebra, we can see that this is 3 times 4 to the n minus 1. What about the area of each triangle added? I'll call it A sub n. The thing to notice here is that each new triangle is 1/9 the area of the triangle in the previous iteration. If we start with this original equilateral triangle, again, we didn't specify the original area of the first triangle. Let's just call it A0, A initial. Since we divide up one of the sides into 3 segments, it has 1/9 the area. Which means that the area of each new triangle added is A0 divided by 9 to the n being the nth iteration. Here's the fun part. We have a formula for the number of new triangles added, and we have a formula for the area of each new triangle added. So the total area added by each new iteration, I'll call it B sub n, should be the number of triangles added times the area added. Just multiply our 2 formulas together, and we can make this look a little nice with properties of exponents. That's the total new area added in each iteration. We're interested in the total area of the snowflake altogether, so we have to sum this iteration for every value of n. Let's let capital A sub n be the total area of the snowflake after n iterations. That's A0, the original area of the triangle, plus the sum of B sub n. This is a fairly funky formula, but what's great is that we can still use it to find the limit as n goes to infinity. If we were to perform an infinite number of iterations, what would the area of this object approach? And so what we have here is an infinite series. This is something that you would probably come across in Calc 2. This series is what's known as a geometric series, and it has a very nice formula that gives us its result so long as the base in absolute value is strictly less than 1. Here the base is 4/9, so it's all good. Just plugging this into the formula, doing a little bit of algebraic number crunching, we get our answer as 5/8 times A initial, which means the area of this coach snowflake is only 5/8 times the original area of the triangle. It's a shape whose perimeter approaches infinity, but its area approaches a finite value.
If you've taken Calc 2, you can probably figure out that this series, the alternating harmonic series, is convergent. Well, conditionally convergent. If you use the alternating series test, you see that this limit goes to 0 and the terms of the sequence are decreasing, thus this series should converge. But what I think is more interesting is what it actually converges to. ln of 2, that is. Let's start with this sum. You might call it a finite geometric series with n terms. To figure out what this is supposed to be, we'll just call it S. If we multiplied s by x, it would bump the powers of x's by 1. Here's a nice little trick that happens sometimes. Shift all of these terms over by 1, and then subtract these two sums. On the left, we'll get s minus xs, and on the right, all of those middle terms cancel out. We're just left with the 1 and the last term. Factor out the s on the left, divide by x minus 1, and we have the well-known result for the sum of a finite geometric series. Let's treat this result like a function. Right now it's composed with x, but let's plug in negative x to get this result. Let's split up this fraction and subtract the 1 over 1 plus x to the other side. I hope you're ready for some calculus because we are going to take the definite integral of both sides of this equation from 0 to 1. One small thing to note is that we can pull this sum out of the integral with basically no justification since it's a finite sum. This might be a little clunky, but let's just keep in mind the differential here is dx, so any letters other than x are constant with respect to that variable. For example, the antiderivative of x to the k dx, that would be x to the k plus 1 over k plus 1, and then we evaluate x from 0 to 1. You could use a u substitution for this integral, but I think it's easier to just see that if we took the derivative of natural log of x plus 1, it would give us 1 over x plus 1, and so this integral becomes natural log absolute value of x plus 1 from 0 to 1. And this integral we'll just leave alone for now. Here's the fun part. We have this equality, which means the same thing as the absolute value of the left equals the absolute value of the right. Since we're talking about absolute values, we don't need that negative 1 to the n any longer, and absolute values are always greater than or equal to 0. Here's the advantage of not computing that integral. The absolute value of the integral is less than or equal to the integral of the absolute value. This is sort of like the triangle inequality. And since we're integrating between 0 and 1, that denominator, x plus 1, is always going to be larger than 1. So if we just removed it, if we compared it to the definite integral without that denominator, this inequality is always true. Essentially, we're just dividing by less, so the quantity should be bigger. And this integral we can compute. Just add 1 to the power, divide by the new power, substitute in 1 minus substitute in 0, and we get the quantity 1 over n plus 1. Let's collect our thoughts. We have 0 less than or equal to the absolute value of this finite sum minus natural log 2, which is also less than 1 over n plus 1. Now, this is a finite sum, and we were interested in an infinite sum at the start of this video. So let's create it by taking the limit across this inequality. The limit of 0 is 0. The limit of the index of this sum goes off to infinity, creating the alternating harmonic series, and the limit of 1 over n plus 1, that goes to 0. And so we have the squeeze theorem. If the middle part is simultaneously greater than or equal to 0 and less than or equal to 0, it must be 0. Add natural log 2 to both sides, and there you have it. The sum of the alternating harmonic series is natural log 2.
Here's a very interesting formula for pi. But how do we get here? Let's take a look at the series, the sum from n equals 1 to infinity of sine of nx over n. Why look at this sum? Because if we evaluate at pi over 2, we get our sum in question. Then all we have to do is figure out what this series equals will be all set. Getting there might be a little tricky though. We're going to have to use a different representation for sine. In fact, we'll use one of my favorites. We'll use the famous Euler's formula, e to the ix equals cosine x plus I sine x. Or if you like, instead of x, substitute nx. Now, I'd love to just replace the sine nx with e to the I nx. However, in Euler's formula, the sine piece is only the imaginary part of Euler's formula. So the way we get around this, we replace sine with e, however, we restrict it to only the imaginary part. And you might say, okay, so what? We've just changed one series for another. However, this time with the n in the exponent, rearranging things slightly, looks like a fairly well-known power series. In fact, this is the Maclaurin series representation of natural log of 1 minus x, just with e to the ix substituted in. So the imaginary part of this series is negative the natural log of 1 minus e to the ix. Now our job comes down to evaluating a complex logarithm, and if you watched my video on how to do so, you'll be well prepared. We know any complex number can be represented in its polar form, r e to the I theta, where r is the square root of x squared plus y squared, and theta is the inverse tangent of y over x. That gives us that the natural logarithm of any complex number is the natural logarithm of r plus I times theta. So we need to figure out what's r and what's theta for our complex value, in this case, 1 minus e to the ix. We need to figure out what's the real part and what's the imaginary part. Fortunately, again, Euler's formula comes to the rescue. E to the ix is cosine x plus I sine x, so we can reduce the inside of this logarithm to 1 minus cosine x minus I sine x. The real part is 1 minus cos x, the imaginary part is minus sine x. R is the square root of x squared plus y squared. Here the square root of 1 minus cosine squared plus sine squared. Theta is the inverse tangent of y over x. That's the inverse tangent of minus sine over 1 minus cosine. This is a pretty lengthy equation. Fortunately, if you recall, we were only concerned with the imaginary part of this. We don't even need to worry about the real part. We're only looking at the imaginary part, which is the inverse tangent of sine x over 1 minus cosine x. And if you string this all the way back to the beginning, this was connected to the original series by substituting pi over 2. If we plug in pi over 2, we get that sum in question. We also plug in pi over 2 to the other side. That's inverse tangent of sine of pi over 2 over 1 minus cosine of pi over 2. Using a little bit of trig knowledge, that'll be inverse tangent of 1, which is pi over 4.
Here's an infinite sequence of real numbers. The question is, can you find such a sequence so that this equals n for every positive integer n? A tricky question, and to be honest with you, I have no idea how you would go about trying to find such a sequence. This is a Putnam problem, so maybe you're expecting some slick solution, but the way the question is worded, is there such a sequence, might make you think that the answer is no. If we find one example where this supposed fact doesn't work, well then we disprove it. To do that, and for seemingly no apparent reason, let's look at the Cauchy-Schwarz inequality. Since we're talking about sequences of real numbers, we'll just use the Euclidean dot product as our inner product and have this representation for our inequality. How exactly is this helping us? Because this is talking about two different sequences, u sub n and v sub n. Well, let's just look at two versions of the sequence we're asked about by picking different values for m. What if we look at m equals 1 and m equals 2? Let's just throw these two sequences into our inequality. We'd have a sub n to the first times a sub n squared. Properties of exponents, that would be a sub n to the third. And according to our inequality, this should be less than the sum of a sub n to the first squared times the sum of a sub n squared squared. If this proposed infinite sequence did exist, we know how to sum these quantities. The sum of a sub n cubed, well, that would be 3. Squared is 9. That has to be less than or equal to, according to our inequality, the sum of a sub n squared, which is 2, times the sum of a sub n to the fourth, which is 4, and 2 times 4 is 8. And so 9 is less than or equal to 8? I don't think so. That's a contradiction, meaning the original proposed infinite sequence cannot exist. Take a look at this nested sequence starting at pi over 2. Our job is to figure out whether the sum of this sequence squared converges or diverges. I think this is a very interesting problem from the Putnam exam of last year. To make our lives a little bit easier for the intervals we're going to be looking at, let's just find a sub 1 by plugging in a naught to this recursion. That would be sine of pi over 2, which we know to be 1. The next thing to note about this sequence is that it's both positive and decreasing. If we look at the graph of sine x and x on the same plot, we see that between x equals 0 and 1, our graph of sine is always positive, and the graph of sine is always less than the function y equals x. And just visually we can verify that x is greater than sine x, which is to say a sub n is greater than sine of a sub n, and we can see that this means our sequence is decreasing. So we have a sub n is both positive and decreasing. We're looking at the sum of a sub n squared, so it really feels like this should be convergent. But not so fast. Let's look at the Taylor series representation for sine x, and we'll restrict our discussion to x being on the interval 0 to 1. Now that's a lot of terms to work with, an infinite number in fact, so let's cut this off a bit, let's truncate it just using the first two terms and using the remainder theorem. That theorem says essentially that if we cut off our sum at the third degree term, then we need to add on a remainder, an error term if you will, that is a fourth degree term. So that term would be sine fourth derivative evaluated somewhere in our interval 0 to 1 times x to the fourth over 4 factorial. Fortunately, we know how to take four derivatives of sine x. The first derivative would be cosine, and then negative sine, and then negative cosine, and then positive sine once again. So the fourth derivative of sine x is simply sine x, or in this case sine of c. Something to note, since we're only considering values of c between 0 and 1, and we know sine x is positive on 0 to 1, then that sine term must be positive, 4 factorial is positive, and if we're between 0 and 1, to the fourth power will also be positive. Thus, this entire term is greater than or equal to 0. So we can completely ignore this term via an inequality. What we have when the dust settles is sine x is greater than or equal to x minus x cubed over 3 factorial, so long as we're considering x values between 0 and 1. That was all a bit out of nowhere, considering what we actually wanted to figure out was about the sum of a sub n squared. We want to show whether it's convergent or divergent. One way to show a sum is divergent is to directly compare it to the harmonic series, the sum of 1 over n. If we were to show that our sum was greater than this sum, since the harmonic series diverges to positive infinity, if our sum was greater than that, greater than infinity, well, it must be infinity and it must diverge by comparison. Here's our claim. A sub n squared is greater than or equal to 1 over n. This is our comparison to the harmonic series, since we can just take the sum of both sides. Maybe it's a little clunky to work with a sub n squared, and we've been talking about simply a sub n this entire time. Let's just take the square root of both sides, and we'll restrict our discussion to only n greater than or equal to 1. That way we don't have to worry about plus or minuses. Let's prove our claim with mathematical induction. I think about it like laying up a bunch of dominoes, tipping the first domino over, and seeing the rest of the dominoes fall. Although there are going to be an infinite number of dominoes. It works like this. We need a base case, that's like our first domino, and then we have our induction step where we need to assume if any domino is tipped over, the next one would fall. Those two facts would ensure that all of our dominoes would tip over, and thus the claim would be proven. So let's lay that first domino, let's make our base case n equals 1. Let's just check that 1 satisfies our inequality. A sub 1 is greater than or equal to 1 over the square root of 1. Is this true? Well, a sub 1 was 1, and 1 over the square root of 1 is 1. 1 is greater than or equal to 1, and we have our base case. Here comes the induction step. We assume this is true for n equals k. In other words, a sub k is greater than or equal to 1 over the square root of k. That's our assumption. Pretend we have that as a fact. We want to show it's true for n equals k plus 1, or in other words, n sub k plus 1 is greater than or equal to 1 over the square root of k plus 1. If we can prove this, we can sort of backtrack and get that initial claim that our sum is greater than the harmonic series when we compare it to, and the sum would diverge. So let's look at what we want to show. a sub k plus 1 is greater than or equal to 1 over the square root of k plus 1. We know what a sub k plus 1 is. That's sine of a sub k. Through our argument earlier, we had a different representation for an inequality of sine x. We saw sine x was greater than or equal to x minus x cubed over 3 factorial. So let's slip that fact into this inequality. If we can show a sub k minus a sub k cubed over 3 factorial was greater than 1 over square root of k plus 1, then that would imply our previous step, which is what we want to show. Since we finally have some a sub k's, we can actually use our induction hypothesis, as it's called. We're assuming a sub k is greater than or equal to 1 over root k, so let's slip that into this inequality. Now we want to show this. 1 over root k minus 1 over root k cubed over 3 factorial is greater than 1 over square root of k plus 1. It's a bit of a mouthful and a bit clunky, but if we prove this, that would imply our previous step, which would imply the previous step, which is what we want to show. At this point, it's pretty much coming down to algebra. Let's just rewrite this inequality using properties of exponents, and then what we can do to clean this up is multiply every term by a k to the 3/2 power. K to the 3/2 over k to the 1/2, that's k. The k to the 3/2 would clear in the second term, and on the right-hand side, it's just going to be looking like this. Now to get rid of those roots, let's just square both sides so those roots will clear on the right-hand side, and we'll just have to distribute out the left-hand side. Multiply both sides by k plus 1, and then distribute once again. What we'll see is some k cubes popping out here, but fortunately k cube on the left and the right cancel out. Moving everything to the left side so this is greater than or equal to 0, we have this clunky polynomial. Fortunately, we can clean it up a little bit by multiplying everything by 36. And hopefully you're up to date with your factoring by grouping, because this does factor pretty nicely. And the solutions of this inequality are k equals 1/3 and 1/8. Fortunately, we're only interested in k in the natural numbers, starting at 1 and greater, and thus this inequality will hold true for all k in the natural numbers. Basically, a positive times a positive is a positive, which is greater than or equal to 0. So let's see what we did here. We showed that this inequality was true for all k in the natural numbers. That implied our previous statement, which implied our previous statement, which was basically what we wanted to show, and our induction step was proven. And our comparison is complete, thus the sum of a sub n squared is greater than or equal to the sum of 1 over n, which is the harmonic series. We know this to be a divergent series. It's really a p-series with p equals 1, and the conclusion is that our series diverges. When I first came across this so-called Grandi's series, I didn't think a whole lot of it. By using our standard methods, this series clearly diverges. Just use the test for divergence, see that this limit doesn't exist, and there you go. I saw the unrigorous attempts at trying to sum this series. If you arrange parentheses like this, it looks like we're just adding up a bunch of zeros, and so this sum should be 0? But if you arrange parentheses like this, it looks like we're adding up 1 plus a bunch of zeros, and so the sum should be 1? Clearly associativity wasn't going to do the job. The next unrigorous method tries to use the distributive law. Just do 1 minus this sum and distribute. You would basically distribute the negative, and so we would end up getting 1 minus 1 plus 1 minus 1. That's just the original sum we started with. And so 1 minus the sum equals the sum? Or 1 equals twice the sum? And the sum is 1/2? Like, no way, that's totally ridiculous. Adding and subtracting a bunch of 1s to get a half makes no intuitive sense, and I was about to write this off as a fluke. But as I dug deeper, this 1/2 kept showing up. There's this idea of Cesaro summation, which instead of doing a traditional sum, which is the limit of the partial sums, it takes the average of the partial sums. This summation is sort of like a less restrictive convergence, and when we apply it to our Grandi series, you get 1/2. And it turns out there are numerous methods that when applied to this series, you get 1/2. But despite all this, I still wasn't really convinced yet, until I started to look at the geometric series. The good old geometric series x to the n summed from n equals 0 to infinity, this equals 1 over 1 minus x, so long as x is between -1 and 1, not including those endpoints. If we substituted x equals -1, we get our Grandi series. But we can't substitute -1 into the formula 1 over 1 minus x. That's outside the interval of convergence. Well, it's really right on the tip of the interval of convergence. So if we can't evaluate right at x equals -1, what if we approached it? What if we did limits? If we let x approach -1, then the geometric series approaches the Grandi series, and its sum approaches 1 over 1 minus 1, or 1/2. That's pretty interesting, but we know limits as x approaches a can be different than the function evaluated at a. I was just about to give up when I stumbled across this idea that has become very popular at explaining these type of weird phenomenon, this idea of analytic continuation. That interval of convergence, -1 to 1, think of that as like a domain of this function. We want to extend that. We want to push the boundaries to include more things. A way to do that is through Taylor series. Taylor series give us great approximations for a function around a certain value. You see, the sum of x to the n is basically like a Taylor series centered at a equals 0 for the function 1 over 1 minus x. Well, let's come up with a different Taylor series centered around a different value so we can push or move that domain, that interval of convergence. To make it alternate like our Grandi series, let's just substitute in negative x to get the function 1 over 1 plus x. We'll find the Taylor series for this centered at a. How do we do that? Well, we need to take derivatives of this thing until we see a pattern, basically, and then substitute x equals a. The 0th derivative is the function itself. You could take another derivative using the reciprocal rule, another derivative using the reciprocal rule, and if you don't combine anything, you start to see this alternating pattern as well as a factorial shows up. And it looks like after doing repeated derivatives, the pattern f nth derivative evaluated at a is n factorial over 1 plus a to the n plus 1. Let's just slip this into our Taylor series formula, the sum from n equals 0 to infinity of that derivative we just found times x minus a to the n over n factorial. This is pretty nice because once we substitute this in, a bunch of stuff cancels and we get this nice simplified Taylor series. What you might notice is that if we let a equals 0, you just get the good old geometric series. So the geometric series is sort of just centered at 0. But centering at 0 didn't work because of its interval of convergence. We want our interval of convergence to be around x equals 1. Why 1? Well, that's because if we substitute 1 into this, we get our Grandi series. So we should probably pick a to be something close to 1. There's many choices we could use here. Let's use 3/4. If we substitute 3/4 for a and do a ratio test to see what the interval of convergence is, we see that x equals 1 is indeed inside this interval. So we're all good. Now the fun part. This Taylor series is a geometric series, and we know how to sum it. The way we sum geometric series is a over 1 minus r. A is the first term of the series. R is that common ratio. Let's just substitute these values in. A little bit of algebraic simplification, and what do you know? We get 1 over 1 plus x, which we should. So if we substitute in x equals 1 via an analytic continuation, this equals our Grandi series, and its sum converges to 1 over 1 plus 1, or 1/2. I'm still not entirely sure that I'm convinced, but this argument is pretty compelling.